Advantages of cadmium telluride, cadmium zinc telluride. The disadvantage is that non-unity segregation of zinc, which means if you grow a cadmium zinc telluride ingot or a crystal of suppose 10 centimeter, the zinc concentration basically changes with distance of the or the length of the ingot. So that means zinc concentration, we cannot keep it constant throughout the ingot. So we have to cut down or throw some of the portion of the material, and we have to keep the portion where zinc concentration is uniform. Rest is throwable. And it has got so many subgrain boundaries. That is, subgrain boundaries are basically dislocations in the material, and they make networks, dislocation networks, and all these things inside the material. Those are basically killing factor for carrier to propagate through the device thickness. So we have to get rid of these subgrain boundaries to get a better material or to increase the yield of high quality detector. So these subgrain boundaries or dislocation network basically kills the device properties. And we have another problem, that is large number of tellurium inclusions. When we grow the crystal, we see there are a lot of lump of telluriums. They precipitate inside the material, and those precipitated tellurium inclusions basically performance limiting factors in the device properties. It hinders the charge transport of the material, and as a result, you will not get a good quality device. And what is good quality and bad quality device? For radiation detector, mainly for gamma rays, we basically consider it is about 1.3 MeV to lower part around 15, 20, 30 keV. So middle of that is about 662 kV. So we consider 662 kV as a yard to quantify the quality of the detector response. So that means if a material has got resolution, energy resolution at 662 kV, 5% means material, the detector is not good. If the energy resolution at 662 kV is less than 1%, that means it is high quality detectors. So we have to have very sharp peaks to get to make a very good detector and make a very good device. So basically 1 to 2% is basically very high quality detector that gives you enormous amount of information about radiation environment around us. If it is more than 3%, we lose many information about the environment and any kind of radiation around us. So our main goal is to make the CdTe detectors between 1 to 3%. Now, what is the path to success to advancement of CdTe? Very first thing is purification of raw material. We have to have very high purity material, and for your information, the purity means it is called 99.999999 percent pure. So this kind of material we start growing this crystal, or industry start growing crystal with initial purity of 6,9 purity. What is 6,9 purity? 6,9 purity is 99.9999. Total number of nines should be 6. So that is called 6,9 purity. So they start with high purity material and then crystal growth. And then we have to have surface processing for device fabrication, then metallization, then we have device structure. So there are so many factors for the advancement of CdTe. But the main factor is purification of raw material and the crystal growth. Without these two components, one cannot, if you do not have crystal, you cannot make detectors. As simple as that. Now there are various growth techniques, and majority of the crystals, whether it is radiation detector for any other applications, they can be grown from different techniques, which is called melt growth, vapor growth, and solution growth. What is melt growth? Melt growth means you melt the whole material and then solidify from bottom to top or top to bottom. That is called directional solidification. Vapor growth means you evaporate and slowly deposit the evaporated material, and that basically gives you the growth of the whole ingot. And solution growth means you grow the crystal from a solution. Means, for example, sodium chloride, that is our salt we eat every day. You can grow either by melting, the melting point of sodium chloride is about 800 degrees centigrade, or you can dissolve it in water, make a saturated solution and let the solution evaporate little bit out, and you can see some crystals are growing at the bottom of the solution. So that is called solution growth. So you are basically growing the crystal from a suitable solution. Any questions so far? So melt growth techniques again has got various techniques. You can grow by using melt growth technique. One is Czochralski, that is not suitable for cadmium zinc telluride growth. This method is suitable for silicon growth. So people all over the world, whatever you are using electronics component has got silicon. And all the silicons are being grown by Czochralski method. There is another technique called Bridgman method and a traveling heater method. I will talk little bit about Bridgman method and traveling heater method because these are the two techniques people are using to grow cadmium zinc telluride or cadmium telluride. Now this is a Bridgman growth method. What is that? It is very simple. Crystal growth is basically very simple technique. And what is this? This is the ampule where you grow the crystal. You put the material inside the ampule and then seal it under very high vacuum, 10 to the minus 7 or 10 to the minus 8 torr. Under high vacuum, once you seal it, you put it inside the furnace and increase the furnace so that the whole material is molten. And through the furnace, if you see the temperature profile here, the temperature is low here and high here on the top. So if you keep on lowering it down, once it crosses the melting point of the material or solidification point of the material, it starts crystallizing. So that means you are basically lowering down the ampule and let it go towards the lower temperature side so that it solidifies at the tip and then kept on solidifying to the top of the whole ampule. So by this technique, you can grow the whole crystal or solidify the whole crystal, and this is called directional solidification. You are basically solidifying in one direction. That is opposite to the ampule's direction. Ampule is going down, your crystal is growing up. Now, for cadmium zinc telluride, there is a big problem here. Cadmium has got very high vapor pressure. What does that mean? When you grow cadmium zinc telluride or when you melt the whole material, melting point of cadmium zinc telluride is about 1130 degrees centigrade. So when you melt the whole material above 1130 degrees centigrade, since cadmium vapor pressure is higher than zinc and tellurium, cadmium tries to evaporate out from the top of the molten zone. And they start depositing over here. So that means when you grow the crystals, you will grow it with less amount of cadmium. That means you are losing a lot of cadmium during this process. And how to get rid of those things, those evaporated cadmium? One is if we can put some container here and put some cadmium here, that means this cadmium will start evaporating, and that will compensate the evaporation from the melt. So this if we put some cadmium here, that itself will build up enough pressure so that it will resist other vaporizing the material cadmium from the melt. So this is one technique. Another technique is that we can basically encapsulate, or we can put some material so that it floats on the top of the melt without reacting to the melt. And that liquid will prevent evaporation of cadmium from the melt. So what is that? So we can put cadmium over pressure. That means we can put some cadmium container here that is at high temperature, and that itself will create cadmium vapor, and that will prevent any loss of cadmium from the melt. Another is liquid encapsulated. That means we put some liquid on the top of it so that it will prevent evaporation of cadmium from the melt. And what is the third technique? Third technique is we can grow the whole material. Instead of putting vacuum, we can put the whole ampule inside a pressure vessel. If we put very high pressure, we can prevent lot of cadmium evaporation from the melt because we are already putting a lot of pressure on the top of the melt. So that means we are having under high pressure Bridgman growth. And another technique is the low temperature growth. What is that? We can grow it from solution like sodium chloride, I said. If you heat sodium chloride to its melting point, 800 degrees centigrade, chlorine will try to evaporate from sodium chloride. But you can grow the same sodium chloride, very pure and very stoichiometric material, if you just dissolve it in water and you are let the water evaporate and the crystal will keep growing inside the solution. So these are the different techniques one can get rid of this cadmium evaporation from the melt, and industry are also using this kind of techniques. So how industry started? Industry basically started with high pressure. The first industry which came up, that is EV products, they started with very under high pressure growth of cadmium zinc telluride. That means they started growing that crystal under a high pressure chamber. So as I said, most of the material, for example, for cadmium zinc telluride, it is under 1120 to 1130 degrees centigrade melting point. So what is another disadvantage of this? At this high temperature, when you put it in a crucible, the crucible we use generally is a quartz ampule. And these quartz ampules are not really that high pure material than the material we are growing. So what happens at that high temperature, the impurities which has got inside the crucible, they start migrating to the material, and the material will be basically impure, and the impurities comes from the crucible. So we will try to avoid, or people try to avoid, to grow the crystal with such high temperature so that we can get very low amount of migration of impurities from the crucible itself. As because we are starting with very high purity material, that is 6,9 purity material, and the crucibles are not really that high pure. And what is traveling heater method? Traveling heater method is basically a solution growth technique, very precise control of solution growth. If you see this ampule, we put kind of disk of tellurium here. The tellurium melting point is about 450 degrees centigrade. And what does tellurium does? Tellurium does the same function as water does for sodium chloride. Tellurium is basically like water for cadmium zinc telluride. It dissolves cadmium zinc telluride, and we grow the crystal from the cadmium zinc telluride and tellurium solution. So what does it do here? Suppose this is about 1 inch or 2 inch or 3 inch wide tellurium zone. And the temperature we maintain so that the temperature is higher on the top surface and lower on the bottom surface of this tellurium melt zone. At a particular time, this tellurium is basically saturated. Saturated means it is dissolving as much as cadmium zinc telluride from the upper part of the ingot. Now, if we move the heater, this is a heater. If we move the heater upwards or pull the ampule downwards, what happens? Since the temperature is higher here and temperature is lower here, it will dissolve some excess material from the upper cadmium zinc telluride ingot, and then the extra material will be deposited near the bottom of the ingot or bottom of the tellurium rich molten zone. So what happens after some time, it will keep on eating the dissolving material from the top and keep on depositing in the bottom as we move the furnace up or pull the ampule down. So what happens, the tellurium started over here, and after the growth run, tellurium moves over here, and we can grow the whole crystal from the tellurium rich melt. So it is a solution growth technique. And since the melting point of tellurium is 450 degrees C, we can technically grow these crystals above 450 degrees C. But at that low temperature, the rate of dissolution of cadmium zinc telluride in tellurium is very low. So what people generally use, they grow at 850 to 900, 800 to 900 degrees centigrade. So at that high temperature, it dissolves very fast so that you can grow the crystal very fast. So instead of growing the crystal at 1130 degrees centigrade, now we can grow by traveling heater method at 850 or 900 degrees centigrade. And this is called traveling heater method. Now I should mention that you see the temperature here. Temperature here is room temperature. Temperature here is room temperature, and temperature at this peak is about 850 degrees centigrade. So that means from here to here, if you see the temperature gradient, it's very high. It is more than 125, 150 degrees centigrade. So I want you to remember that high temperature gradient, which we will talk a little bit later about that. Now, what is the advantages and disadvantages of Bridgman growth and THM growth? The Bridgman growth advantage is it is a very easy technique. You just melt the material and lower the ampule through the temperature profile, and it will grow. And it is simple and inexpensive technique. Whereas for traveling heater method, it is a tricky technique. Those who are not really experienced, they cannot really grow very good quality crystal by traveling heater method. And advantages are, since it is a low temperature operation, you can expect that very minimum amount of impurities that will migrate from the crucible to the crystal. And since it is a low temperature, whenever you cool down any material from high temperature to low temperature, you basically generate thermal stress in the material, whether it is glass or any other material. So if we grow about for 1100 degrees, 1130 degrees centigrade and cool down to room temperature, we will generate a lot of thermal stress, which stress basically generate those dislocation walls inside the material. But if we grow from lower temperature, the amount of stress will be much less as compared to the melt grown technique. So you will have less amount of performance limiting defects, those are dislocation walls and other defects. And another advantage of is that the tellurium basically absorbs many impurities. So tellurium is basically act as a sink. So whatever impurities was there in cadmium zinc telluride, tellurium basically sucks all the impurities and leaves behind the most pure material as cadmium zinc telluride when you grow it by THM technique. The only disadvantage is that the crystal grows at a very slow rate. For Bridgman growth, you can grow the crystal at a rate of 3 to 5 centimeter per hour. But for traveling heater method, growth rate is about 3 millimeter per day. Why it is so slow? Because as I said, we have to give some time to dissolve the cadmium zinc telluride into tellurium and deposit near the bottom of that zone. So dissolving time is a lot more than just solidifying any material. So we have to give a lot of time for dissolving the material to tellurium rich zone. That is why it basically limits the crystal growth speed. So we generally grow 3 to 5 millimeter a day. But even the growth process is so slow, most of the industries today, those who are making high quality detector grade cadmium zinc telluride or cadmium telluride, are using this traveling heater method, although the growth rate is very low. Now, how did it start commercialization? In 1984, Acrorad in Japan founded this company and they started growing cadmium telluride. And as I said, cadmium telluride is not good for homeland security application, but it is good enough for medical imaging purpose. So they started this company for cadmium telluride only. Since 1984 till today, they are growing cadmium telluride only. They are not growing any cadmium zinc telluride. They are not competing with homeland security. They are focused for medical imaging applications. So in 2011, Siemens is a big player in making medical imaging machines. What they did, they purchased this Acrorad so that they will have enormous amount of supply of cadmium telluride. So they do not have to depend on other supplier of cadmium telluride. So what they did, they purchased the whole company and started using those cadmium telluride for their medical imaging machine. Now, how did it start? In 1984, it started, and 3.2 centimeter diameter. These are all grown by THM. 3.2 centimeter diameter, they started from 1988 to 1998. So think about the timeline. 10 years, they were stuck to 3.2 centimeter. From 1995 to 2002, they started growing 5 centimeter diameter ingot. From 2000 to 2007, they were growing 7.5 centimeter, and maybe 2007 onwards, till now, they are growing 10 centimeter, that is 4-inch diameter ingot. So if you see the timeline of this increase of ingot diameter, 10 years they took from 3 centimeter to 5 centimeter. So you can, from here, you can well understand that tellurium, traveling heater method is not really very straightforward technique. For 3 centimeter to 5 centimeter, they took more than 15 years to just increase by 2 centimeter in diameter. And the top figure is about 3 inch, that is 75 millimeter diameter cadmium telluride ingot, and this is 4-inch diameter, that is 100 diameter of cadmium telluride ingot, that is Acrorad is producing right now, is 10 centimeter diameter ingots. And these are 18 kg and 3-inch are 7.5 kg kilogram. In 1992, EV products started producing cadmium zinc telluride. And how did they do? They started growing by Bridgman method, but under high pressure. So what they thought that they did not want to spend long time for research and our development. High pressure bridgman is a straightforward method. Only thing is that capital cost is very high. High pressure bridgman growth unit are very expensive. So they had money, they started with very highly expensive instrument to make sure that the very product they come out will not have any problem. So they started with high pressure bridgman by growing cadmium zinc telluride, and they started marketing since 1994 or 95. And in 2013, a company called Chromec, they purchased EV product. By the way, right now, EV product do not use high pressure bridgman technique because high pressure bridgman or bridgman technique CdTe do not match the quality if you grow by THM technique. So they discarded high pressure technique, and now they are also growing by traveling heater method technique. And in 1999, Redland Technology in Canada, they started growing cadmium zinc telluride by traveling heater method technique. And in 2021, about 1.5 years back, Canon is also a big player in making whole body scanner medical imager with cadmium zinc telluride. So they wanted to be self-sufficient, so they purchased Redland in 2021, and they are also continuing growing the crystal by traveling heater method. So all the major companies like Chromec, Acroded or Siemens, Canon or Redland, they are all growing by traveling heater method. Although the growth rate is very high, very low, since this material, this technique gives the highest quality cadmium zinc telluride detector grade material, everybody is going for traveling heater method technique for production of cadmium zinc telluride or cadmium telluride. Now there is another problem here. Once you grow the crystals by by traveling heater method, as grown material do not really work as a detector material. So what they do, they have to go for post-growth annealing. So they cut wafers and put it in the furnace for a long time, anneal it at different cadmium pressure or tellurium pressure, whatever it is, we do not know. That is the industry's secret. And by doing that, they could get rid of the tellurium inclusions. After annealing, you cannot see those tellurium inclusions inside the crystal. And they claim that they get better charge transport properties, and then they make it as a detector material. So once you grow the crystal, it does not work as a detector. You have to go through the post-growth annealing. In 2009, ICX radiation first reported high-quality detector grade CdTe, cadmium zinc telluride, grown by THM technique. So they first said that, okay, we do not need any post-growth annealing. We can grow it and just use it as a detector. So what they did, as I said before, for traveling heater method, the temperature gradient is generally people use 100 to 150 degrees centigrade per centimeter. So when you have that high temperature gradient, you may come out with a lot of problem. For example, suppose you have a 1 centimeter thick glass block and you immediately put it in 100 degrees centigrade or boiling water. The glass block will immediately crack, right? Because the glass has got very low thermal conductivity. And moment you put the material inside the boiling water or the glass inside the boiling water, the surface will see the temperature 100 degrees centigrade. But inside the glass, it will take some time to reach the temperature because thermal conductivity is very low. That means you are basically creating very high temperature gradient within the glass. And what does that do? That eventually gives lot of thermal stress, and eventually it cracks the glass. But if you put the same volume of diamond inside boiling water, the diamond will not crack. Why? Because the diamond thermal conductivity is very high. So immediately the temperature will be uniform all through the diamond. So there will be no temperature gradient inside the material. So material will not be cracked, or it will not generate any defects because of thermal stress. So the problem with cadmium zinc telluride is it has got very low thermal conductivity. That means low thermal conductivity material, you cannot really grow under very high temperature gradient. So in ICX radiation, what they did, they started growing this THM growth technique under very low temperature gradient, that is 15 degrees centigrade per centimeter. As a result, the material was having very less thermal stress inside the material, so very low amount of dislocations and whatever it is. And they eventually get as grown detector get material. So you do not have to post growth anneal or do anything. So you can just cut it and make the detector. So in 2013, Redland Technology also started following ICX radiation. They published in 2009. And they also started working on developing their technique so that it grows and acts as an as-growth detector material. In 2013, they reported first thing. 2014, in conference, they reported that they have achieved as-grown detector growth material, but we are not sure whether they are still doing the research or they are marketing that product. So what was the development of CdTe? For last 3 decades, when the EV products started growing CdTe with high pressure Bridgman growth technique, their mu tau value was 10 to the minus 4 centimeters square per volt. And today, Redland producing material by traveling heater method, this is 3 to 5 10 to the minus 2 centimeters square per volt. So the mu tau, you can see it is almost 2 order of magnitude higher than in today than it was 30 years back. And the major advantage of the material or cadmium zinc telluride detectors, whatever you say, is basically because of the improvement of raw material. People do not acknowledge that. Most of the people say, oh, we have done good quality crystal and this, that. But basically, the advancement was mainly because of the raw material improvement. The purity of the raw material has improved drastically once 5N Plus, that is a Canadian company, started producing cadmium telluride and cadmium zinc telluride high purity material. And they are the supplier all over the world for the raw material of cadmium zinc telluride and cadmium telluride. Even cadmium telluride is being used for solar cell application. There is a company called First Solar. They are producing cadmium telluride based solar panel. 5N Plus also produce or supply the same material, cadmium telluride, to First Solar company. So the main credit really goes to 5N Plus, because without raw material, good quality raw material, you cannot really improve any crystal growth. Even if you grow very high quality crystal, if your material has a lot of impurities, it does not really work for good quality detector, even the crystal quality is very high. So the CdTe technology is still suffering from 3 critical issues I mentioned already before. Non-unity segregation of zinc, that means zinc concentration varies along the length of the ingot, subgrain boundaries, and large number of tellurium inclusions. So what does that mean? The overall yield of detector grade from a given ingot of CdTe, cadmium zinc telluride, is about 20 to 25%. And if you want to have a very high resolution detector between 1 to 1.5% and 662 keV, it is the yield is less than 10%. Actually, it is about 5% or less. So that is why the high quality detector grade CdTe is so expensive. It is, I think, about three times expensive than gold today. Now, if we see the compositional variation, if you grow by traveling heater method, you see the zinc, this is the zinc concentration along the length of the ingot. You can see the zinc is almost uniform near the middle of the ingot. That means only 1/3 of the ingot, grown ingot, is useful for fabricating detectors. That means 2/3 of the ingot you have grown, you have to cut it and throw it. That goes to the garbage. So your cost is basically directly increases by 3 times because you have to throw 2/3 of the material to make detector. And out of this 1/3 of the material, you will have lot of defects like tellurium inclusion, dislocation walls. And based on that, your high quality detector yield is even less than that. And if you grow by Bridgman technique, you see the concentration of zinc is kept on decreasing from bottom to top. The bottom is the where crystal started growing, first grew and then it grew on that upward. So as you go from bottom to top, your zinc basically keeps on decreasing. So for Bridgman grown, you cannot get anywhere along the length of the ingot uniform zinc concentration. So the yield is really awful. That is why people do not use Bridgman grown technique. People go for industrially. Traveling heater method is the right technique that is being employed by different industries. Now, about the subgrain boundary network, what does that do? If you see this picture, these are the X-ray topographic image of cadmium zinc telluride from 7 different vendors all around the world. And you see these white and black lines, networks. These are all basically subgrain boundary or dislocation walls. So if you see the right corner, that is V3, there is a small amount of portion which does not have any defect or any dislocation. So if you make a detector from this region, this detector will be high quality. That means about 1 to 1.5% resolution at 662 keV. And if you make a detector out of this area, it will be more than 5% or. So what does that mean? That because of the presence of subgrain boundary network, yield of high quality detector, that is between 1 to 1.5%, is really very low. 3 to 5% you can get out of these materials, but not 1 to 2%. And what does all these subgrain boundary network do? Suppose for medical imaging application, if you do not take any picture, without any picture or any object, you see these are your subgrain boundary network or the dislocation walls. And if you take the picture, medical imaging picture, using that material, you see this is the picture. This is basically a pori shell. And you see in this picture, those subgrain boundaries are visible. That means if you have any kind of cell growth or anything inside those, because of this subgrain boundary network, which is also present in the picture, will be lost if it is a small grain growth or some cell growth. So what they have to do, they have to do the correction, post-growth, post-imaging correction. They use softwares to get rid of those background noise, and then they get the actual picture. So you have to do all those image processing after you take the image. So that is the biggest advantage of cadmium zinc telluride because of the presence of subgrain boundary network. And what about the device performance for homeland security purpose? Suppose this is the X-ray topographic picture of a CdTe detector. This is another detector. You see this detector on the right hand side has got lot more defects than the left hand side. So the resolution is 2.3% at 662 keV for this detector. Whereas if you have a material with very high density of defects, your resolution is 4.2%. That means your detector is getting worse because of the presence of those subgrain boundary network. And if you have a detector without having this subgrain boundary network or dislocation network, you can expect the detector resolution to be between 1 to 2%. So again, I should say that getting 1 to 2% resolution with cadmium zinc telluride, the probability is very low because of this subgrain boundary network. And what about the tellurium inclusions? If you see tellurium inclusions, these cadmium zinc telluride are basically opaque material. In visible light, you cannot see through, but if you see through infrared light, it is transparent in infrared light. So what people do, they do the microscopy in infrared light, and they can see those. You see the black dots; those are basically tellurium inclusions. And what does it do? They have calculated that how much should be the resolution if you have certain amount of tellurium inclusions of particular size. For example, if you have 10 to the power 4 per centimeter cube tellurium of size 20 micron, your energy resolution at 662 keV will be more than 2%. That means if you want to have a detector with 1% resolution, you cannot basically have that many 10 to the power 4 per centimeter cube tellurium with size 20 micron. So these are basically killing defects for getting the high quality detector. So that means what? If you have to have a 1% resolution, you can probably take 10 to the power 3 per centimeter cube, 20 micron, maybe 5 10 to the power 4, 10 micron diameter, and so on. So once it crosses those values, your resolution getting worse and worse. So this is the direct impact on the energy resolution of the detectors on tellurium concentrations. Now, as I said, that once you do the annealing, post-growth annealing, you get rid of tellurium inclusions. If you look at those samples through infrared imaging, you will see there is no tellurium inclusion, no black spot in the transmission image. But there are some defects which you cannot see in infrared microscopy. They produce some bigger defects. These are all 500 to 600 micron diameter, big defects. Those defects are only visible through etching of the surface or through X-ray topography. But in infrared imaging, it will be very clean. And what those defects do, if you see the trash transport properties across those defects, you see the black spots. These black spots are basically because of charge transport. It is basically hindering the charge to pass through the detector and creates a black spot. So this is the actual picture of the defect etched surface, and this is the image of the X-ray response. That means the response of the detector in that area. The black spot means you do not have any response, and the white spot is you have the maximum response. So those defects, although these are clean or not visible in infrared imaging, those are basically killing material for hindering the charge transport in the material. So even though it looks clean after post-growth annealing, they create even larger defects. So on the first hand, if you can reduce the number of tellurium inclusions in the material, you are good. Now, what are the paths to find a better material? Can we further improve the CdTe growth? People say it has already been improved for more than 3 decades and it has reached a plateau because you cannot improve further CdTe growth because you cannot basically change its thermal conductivity. Thermal conductivity is its intrinsic property. You cannot change the thermal conductivity of the material. So for the 3 decades, people have improved crystal growth, people have improved the starting material impurity and all these things, purity. But those problems, these dislocation walls and tellurium inclusions are still there. So those three major problems could not be solved, although it was reduced a lot. So what is the third path? Second path, find a new material alternative to CdTe. And research is still on. People are still looking for a better material compared to CdTe, but so far nothing is commercially viable. Another path is, can we improve CdTe by using some lattice hardening component? Lattice hardening component, what is lattice hardening component? Means we can put some material inside CdTe so that it will stop generating those dislocation walls in the material. So we found that if we add selenium, that serves the purpose. And we have seen that the selenium, if we put little bit amount of selenium in cadmium zinc telluride, we can drastically reduce the tellurium inclusions. We can drastically reduce the dislocation walls. Actually, it is free from dislocation work network, the cadmium zinc telluride with selenium. And it has got better compositional homogeneity as compared to cadmium zinc telluride. So cadmium zinc telluride selenide, once you put selenium, it becomes cadmium zinc telluride selenide, is far more superior to cadmium zinc telluride as far as defects are concerned. And people are doing research on that material to get better and better detector grade CdTe, cadmium zinc telluride selenide. And as I said, that composition is uniform in CdTe. Subbrain network problem is resolved with CdTe and it contains very less amount of tellurium inclusion. So cadmium zinc telluride. Cadmium telluride was the first member of nuclear detector material community. Cadmium zinc telluride is the second generation of cadmium telluride. Now cadmium zinc telluride selenide is the third generation material for improvement of radiation detector and its application. And if you people are interested, I can talk more about cadmium zinc telluride selenide in my next talk, given an opportunity. And I will discuss more about this. And this material was invented by our team. I was in BNL and the BNL team, we invented this material. We'll talk in details in the next possible talk. And thank you for your kind attention. Any question is welcome.
Thank you so much, Dr. Roy. And the floor is open for any questions. That was very detailed talk, Dr. Roy. Very interesting.
Any question from any students?
Any students or faculty?
Yes, this is Alexander Agariwa.
Mm-hmm.
I was wondering for the sub-grain boundaries, we need them reduced, or doesn't matter?
Pardon? What did you say?
The subgrain boundaries, how do we
Mhm.
reduce them?
How do you reduce them?
Yes.
Yeah, that is called lattice hardening. Basically, to generate those dislocation walls, you have to have some activation energy to generate that, right?
Right.
Suppose you have a 5 feet bar and one is 2 feet bar. You will need less activation energy to jump 2 feet and need more activation energy to jump 5 feet bar, right?
Right.
So what selenium does, it increases the activation energy for producing the dislocation walls. So once you increase the activation energy, it cannot generate until and unless you reach that activation energy. Just like suppose for stainless steel. In iron, you put chromium and nickel and make stainless steel, right? And you make it more harder than pure iron. Is that right?
Correct.
So that is the same explanation. It goes for selenium in cadmium zinc telluride. So those are basically lattice hardening element, which increases the activation energy for developing or generating the dislocation walls.
Okay. Thank you.
Mhm.
Any other questions? Looks like there are no questions. So thank you so much again, Dr. Roy, for your time. And again, I apologize for this confusion. And so you said you're going to have a part two of this talk?
Yeah, I can talk a little bit about cadmium zinc telluride selenide. If somebody